This video covers section 11.3, geometric sequences. We have three objectives in this section. We're going to start by finding recursive as well as explicit formulas to represent geometric sequences. We will solve applied problems using geometric sequences, and then we'll finish with geometric means. So let's start by defining what is a geometric sequence. If you remember, in the previous two sections we were dealing with arithmetic sequences. Arithmetic sequences were sequences in which you added to get to the next term in the sequence. You added a fixed constant, which we called a common difference. A geometric sequence uses a similar idea, but instead of adding or subtracting each time, you are multiplying by a fixed number. The number that you multiply by we call the common ratio. So here's an example of a geometric sequence, 1, 2, 4, 8, 16. We can see that each time it's doubling. It's multiplying the previous number by 2. So to progress through that sequence, you multiply the previous number by 2. We call this number the common ratio because if you take any two consecutive terms and divide them, then you get the ratio of 2, as you can see here. I took a2 divided by the previous term, 2 over 1, that's 2, a3 over a2. Remember again, for the notation, a1 represents the first term, a2 is the second term, a3 is the third, etc. So if you take any two consecutive terms and divide them, you have to get this common ratio. We could write that more generally using this expression here. So we're saying take the nth term, or think of that as the next term, divide it by its previous term, which would be a sub n minus 1. It always has to come out to a fixed number, a common ratio, which we call r. This is the number that you use to multiply to go to the next step in the sequence. Now, let me rewrite that again because it's where we get our recursive formula from. So previously I wrote that a sub n divided by a sub n minus 1 always has to be equal to r. If we simply multiply both sides by this a sub n minus 1, you get a sub n, the next term, is r times the previous term. And that is the formula that you see here. This is the recursive formula for any sequence, or for any geometric sequence, I should say. Now, one restriction too I should mention is that in order for it to be geometric, the common ratio cannot be 0, and we also restrict that it's actually not able to be 1 as well. So an example of that would be if I just wrote the sequence 5, 5, 5, 5, and it's always 5. We don't consider this geometric. It does have a common ratio, but the common ratio is 1, and so we would consider it to be a bad example, so we just throw that one out. We don't consider that to be geometric. Okay, so we've got, in this example here, we're given a recursive formula, and we're supposed to start by finding the common ratio and then the first 5 terms of the sequence. Now, you can get the common ratio just by looking at this expression here. You can see that it matches this, except the a sub n minus 1 is in front, but it doesn't matter. This number, the number that's being multiplied, is still your r. r comes out to 5. Even if you didn't notice that, you can still figure it out by just generating each term in the sequence. So let's go ahead and start it. We were given the first term is negative 4. Now this formula says to get a2, you take the previous term. Right, if this is a2, then this would be a sub 1, the term before it, and then multiply it by 5. You multiply the previous term by 5. Well, the previous term was negative 4. So it would be negative 4 times 5, which is 20. And we just keep this pattern going. To get the third term, we take the previous term, which was a2, and multiply it by 5. In other words, we take that. Oh, I lost my minus sign there too. This should have been minus 20 since it was negative 4 times 5. So here we're going to have negative 20 times 5, which just comes out to negative 100. And 2 more to go, so a sub 4 would be a3 multiplied by 5, which is this number multiplied by 5. So negative 100 times 5, which is negative 500. And then the fifth term is the fourth term multiplied by 5, which gives you negative 500 times 5, or negative 2500. So if we look at the first 5 terms, it would be those numbers there. That would be the beginning of our sequence. And you can see just by inspection, just by looking at them, you are multiplying by 5 each time. Okay, let's try a different one. So again, we're given the recursive formula. We're told the first term is 1/3, and A2, the second term, is going to be 1/2 times previous term. A sub n minus 1 is previous term, which in this case is A1. And so that's 1/2 times 1/3. Well, that's going to come out to 1/6. And you just keep that process going. Now, we don't have to keep writing all this work out that I'm writing here. So the important thing is if you can recognize what r is at the beginning, which in this case, 1/2 is going to be the r. Right, that's the number you're multiplying by each time. We can go straight to the next step just by multiplying the previous one by that 1/2. So A3 would be just 1/2 times 1/6, which is 1/12. A4, 1/2 times 1/12, which is 1/24. And the fifth term is 1/2 times 1/, oops, sorry, I'm writing the answer there, 1/24, which is 1/48. Okay, so that gives us the first 5 terms of that sequence. Now, one thing to notice with these 2 examples, notice in the first one that if you just look at the magnitude, the size of the number, these numbers are getting bigger. In other words, they're getting further away from 0. That's going to happen anytime your r value, your common ratio, is bigger than 1 or less than -1. The numbers in your sequence will grow in magnitude. If your r value is between 1 and -1, like if it's a small decimal or a small fraction, then you can see that the sequence is actually going to get smaller. It's actually going to approach 0. So these denominators are getting bigger, but as a fraction, the actual values are getting smaller. So this relates to exponential growth and decay. Depending on when you're completing this lesson, if you've already done logs and exponentials, there is a connection between that. So just like the arithmetic sequences that we did in the previous sections, a sub n equals a1 plus n minus 1 times d, we said these were basically linear. The geometric are going to be exponential, right? And they have exponential growth or they have exponential decay. Okay, so we've done the recursive formula, like that's what we've been using in these examples, but as before, the recursive formula is not extremely useful because if I wanted, for example, in this sequence, if I wanted to know a sub 100, the 100th term, I have to generate all the terms prior to the 100th term to get there. We would like an explicit formula, like this was an explicit formula, for a geometric sequence. Okay, so this next part, it's already typed out in your notes, but I think it might make easier reading if I just kind of start it from scratch. So we're going to try to establish a pattern here. So obviously, we start with A1, just start with that number. To get A2, the second term in the sequence, we know we're supposed to multiply by R. So A2 is really just A1 times R. To get A3, we take the previous term, we take this, and we multiply it by R. It's going to be A1 R times R. Well, there's another way to write that. That's just A1 R squared. To get A4, again, we multiply the previous term, which is this, times R. So A1 R squared times R. Using exponent properties, we would add the exponents, so it would be A1 R cubed. At this stage, you should start to see a pattern. Notice every single value in the sequence starts with A1, and then they have R's that have increasing powers. The very first one you could actually say does have an R. It's R to the 0 power, and then first power, second power, third power. And this pattern is going to continue. So if I wanted to go down to the, let's say, the 7th term, skip down to the 7th term. Well, this is going to start with A1, and then it's going to have R to a power, and notice the power is always 1 less than the index. So in this case, it would be the 6th power. Where that's coming from is because as we move through the sequence, we just keep multiplying by R. So you can see to get the 4th term here, we had to multiply by r 3 times. That's where we're getting r cubed. To get all the way down here, we would have multiplied by r a total of 6 times to get to the 7th term. Okay, but we want to keep this thing going. We want the nth term. So we know it's going to start with a1. It's going to have a certain number of factors of r, and it's going to be 1 less than the index here. The index is n, so the power is going to be n minus 1. This is our explicit formula for a geometric sequence. Notice there is some differences here to the arithmetic, but there's also some similarities. So if I put the arithmetic one out, we had a sub 1 plus n minus 1 times d. So the first similarity is both of them have the first term in them. They also both have the expression n minus 1. In the geometric, the n minus 1 is an exponent, which is what makes this exponential. And then in the arithmetic, it is just a coefficient of the d, which is what makes this a linear expression. Okay, so let's practice using that. I have it rewritten here. And again, we probably should add the restriction here that it's not going to let me write on top of that, but r's are supposed to not be equal to 1 as well. Let's see if it'll let me send that to the back. Oh, that just duplicated. Okay. All right, let's try applying that to this. So it says determine whether it's geometric or not. We got to do that first. If it is geometric, then we're going to find the explicit formula. We'll do this. Okay, so to determine if it's geometric, we need to see if there's a common ratio. So we have to take the ratio of each successive term. You always want to go from, the confusing thing is people will sometimes divide backwards. You need to start with the second and then divide by the first. So it would be 54 divided by 162. If you want, you can just get the decimal or reduce the fraction, but this reduces down to 1/3. Then you need to check the next one. So it'd be 18 over 54. Right, we're always taking the next term divided by its previous term. That one also reduces to 1/3 as well. You can't just stop here. You do actually need to check all of them because it's possible that it changes up later on. So it's a little annoying. It's the chances that I trip you up like that are small, but you should be checking all the ratios. All right, 6 over 18, that is also obviously 1/3, and then the final one, 2 over 6, is 1/3. So up to this point in the sequence, every ratio was 1/3. The ellipsis says continue on in the same pattern, so we can expect all the other ones to continue in the same way. So therefore, it is geometric. And we also know the common ratio is 1/3. And this is where dividing in the proper order is so important. If I would have divided the other way, if I would have taken 162 over 54, we would get the reciprocal of this. But I know the ratio has to be a number less than 1 because the sequence is getting smaller. Right? We said the numbers will only get smaller or closer to 0 if the ratio is less than 1. Okay, so we have that. We also obviously know A1. A1 is 162. So we can go to the formula. So A sub n is A1 r to the n minus 1. We leave that as it is. A1 is 162. And then it's good practice, and sometimes it's actually critical that you put the ratio, the r value, in parentheses, because that exponent has to apply to the entire common ratio here. So anytime it's a fraction or a negative number, it's critical that we have them in parentheses. I know we don't write it back here, but it would probably be good to just always think of it in this form. That would be the safest way to think of it. Okay, so that gives us our explicit formula. It didn't ask us to find anything else. If we needed to find a specific term, a lot of the homework problems will say, find the 8th term. Then you would just plug 8 into this. So you'd have 162 times 1/3 to the 8 minus 1, or in other words, it'd be 162 times 1/3 to the 7th power. Since we're dealing with exponents, anytime you have to evaluate these, you're going to get really messy numbers, either really messy fractions or messy decimals, or maybe really large numbers as well. So in this case, it would be a very messy fraction. But it didn't ask us to do that here. We can stop with this. All right, let's try another one of those. So same problem, just a different sequence. We need to check to see if it's geometric first. So we start with 6 over 3, that comes out to 2. Then 18 over 6, that comes out to 3. Already it's different. We don't have to keep going. We don't have to keep checking here. We can immediately say, nope, this thing it's not geometric. It's not the same ratio, so therefore not geometric. And therefore we're done. We don't need to keep going. If it's not geometric, then we don't have to, there is no, well, there could be an explicit formula, but we're not asked to find it, only if it's geometric for this. So that one is done. All right, one more. So this one's got some fractions in it, and it's got negatives as well. So let's start with, we're going to do the ratio of -2 over 1/2. That comes out to -4. If you do keep, change, flip, or multiply by a reciprocal, then it would be, the next one would be 8 over -2, also coming out to -4. So it looks good so far, but remember, keep checking. -32 over, what am I doing here? Sorry, -32 over +8, also coming out to -4. Then 128 over -32, also -4. So, therefore, it is geometric. We also know the r is -4, and a1 is 1/2. So we can go to the explicit formula. A sub n is a1 times r to the n minus 1, which gives us -4 times, oh, sorry, that's backwards. A1 was 1/2. And again, put the r in parentheses. Since it's a negative number, it is critical for this one that r value be the negative be in parentheses, so that when you apply the power, it's applying it to the negative number. Okay, so this gives us the explicit formula for that. Now, one thing to notice, this sequence alternates between positive and negative values. We call this an alternating sequence for that, and that's going to happen anytime you have an r value that's negative. When you have an even exponent on a negative, then the negative gets wiped out. That's where you get your positives from. And then when you have a odd exponent, that's where you get these negative terms coming in. Okay, let's move on. All right, let's solve an application problem. So this is a problem I like to give to students to just check their intuition. It turns out that geometric sequences, same thing with exponential functions, a lot of times they can defy your natural intuition. So suppose I'm going to offer you a job, and the pay scheme is as follows. You're going to work for 1 month, 5 days a week, so 20 total days, and the first day I'm going to pay you 1 penny. If you keep coming back, the next day I'm going to pay you 2 pennies, and then I'm going to double it to 4 pennies, double it to 8 pennies. So each day I'm just doubling the previous day's pay. So the question is it worth taking this job? Do you feel like you're going to be fairly compensated by the end of the 20 days if you work the whole time? Well, your intuition, at least most people's intuition, would say, no, I'm not going to take that job. That's not worth it. But notice, this is a geometric sequence. By looking at it, we can see that the r value, that we're multiplying by 2 each time. R is equal to 2. We're doubling in this sequence. We can also see that the first term in the sequence is obviously 1. So we know the explicit formula, a sub n equals a1 r to the n minus 1. Let's plug everything into that. So this gives us a sub n equals 1 times 2 to the n minus 1. Now, since the first term is 1, we really don't need to have it written here. We could simplify this. This a sub n is just 2 to the n minus 1. This equals the pay on the nth day in cents. So number of pennies that you get paid on the nth day. So let's plug, we want the 20th day, so we're looking for the 20th term, a sub 20, which would be 2 raised to the 20 take away 1, or in other words, 2 to the 19th. All right, so turns out it's a pretty large number. That comes out to 52,488. And again, that is cents. So divide it by 100, and that gives you $524.88 for 1 day of work. Right? That is just what you're getting paid on the 20th day. The previous day, you got half of this. So you still got, over $250 the previous day as well. And then if we kept going, if you worked another day, you're going to get over $1,000 the next day. So seems to me like, yeah, it's going to start off pretty bad, but you're going to do pretty well at the end. Now, the next natural question, we've answered this. This is the answer for this problem. But the next natural question would be, how much would you make in total over the whole month? And we will address that problem in the next section when we do geometric series. We'll be able to come up with a formula that would immediately tell us what's the total pay over the whole month. Because you do want to look at that. You would want to look at what's the total pay and then average it out over the month. But right now, that looks pretty nice for the 20th day. Okay, let's try a couple more applications here. So on this one, we're given a geometric sequence. We are asked to find the fifth term and the explicit formula. So since we've already got 4 terms, we can easily find the fifth term just by identifying the common ratio. We already know it's geometric, so what are we multiplying by each time? Well, you can clearly see r comes out to 3. 4 times 3 gives you 12, 12 times 3 gives you 36, so we know r is 3. So the fifth term is simply going to be the fourth term multiplied by 3, which in this case is 108 times 3. All right, so that gives you a value of 324. And now we can also build the formula because we know obviously A1 is also 4. So A sub n equals A1 times r to the n minus 1, which is going to be 4 times 3 to the n minus 1. Now this one, I wrote the parentheses. You don't need it on this one because it is a positive common ratio here. But if you're not going to write the parentheses, then you need to at least have a multiplication operator there. So I still think this probably looks better than this. All right, and that's all they asked for on this one. Now, if the problem had said, a lot of the homework problems here, they'll say to find this first, and they may say find the 10th term. Well, I wouldn't actually start with that because the easiest way to find the 10th term would be to get the explicit formula first. Okay, let's try a messier one. So we saw something similar to this 2 sections ago with arithmetic sequences where they just give you 2 random terms in the sequence and you had to go back and find the initial parts. In that case, it was the common difference in the first term. Here, it's the common ratio in the first term. To do that problem, we had to solve a system of equations. Technically, we're going to have to solve a system here as well, but we won't need to subtract the 2 equations. So let's just try setting these up. We know that the third term is 20, so we start with just the explicit formula. A sub n is A1 r to the n minus 1. And if we're looking at the third term, that's going to be A1 r to the power then would be squared on that. Right? The power is always 1 less than the index. But we know the third term is really 20. So 20 is really A1 r squared. All right, that's one of our equations. So go over here, we're going to set up the second one. So the sixth term is A1 r to the 5th power, because again, power is 1 less than the index. Just plugging that into this. And we know the 6th term is actually 160. So we have 160 A1 r to the 5th. Here's our 2 equations. So when we did this before, we subtracted the 2 equations. We're not going to subtract them this time, but let's go ahead and write them over top of each other. like we did before. So what we're going to do this time instead is divide them. Right? If we divide the left-hand side, it's going to be the same as dividing the right-hand side. So we've got 160 over the 20 gives us the 8 for that one, for that side. And then on the right-hand side, the A1s are going to cancel each other, and you just have r to the 5th over r squared. If we use our properties from algebra, we know that we subtract the powers. If you forgot why that's the case, r to the 5th, remember, is really just 5 factors of r over 2 factors of r, and then you compare them up. Those cancel as a 1, those cancel as a 1. You're left with 3 r's, which is r cubed. Right? But the fast way of doing that is just subtract the powers. Okay, so now we need to get r by itself. So I need to get rid of this power. So the easiest way to do that is to use fractional exponents. We're going to raise both sides to the reciprocal power here, the 1/3 power in this case, because we multiply powers here. Power raised to a power you multiply, so 3 times 1/3 gives us a power of 1 on that term. So you have 8 to the 1/3 power. And hopefully we remember that 8 to the 1/3 is the same as cube root. Right? Fractional exponents are really just roots. The cube root of 8 is 2. All right, so we got that part of it. They asked us for the common ratio, and so we got the r value. All right, to find the A1, we do exactly what we did in the previous problems. You just plug it back into one of the equations. Anytime you're solving a system, if you've got one of the variables, you can back substitute to help you find the others. So I'm going to plug back into this one. So we have 20 equals A1, and now I can go ahead and put 2 in for the r. So that gives us 20 equals A1 times 4. 2 squared gives me the 4. Divide the 4 over, and we end up with A1 is equal to 5. Right? 20 divided by the 4 gives us 5. So that gives us everything they asked for, A1 and r. This particular problem did not ask us to find the explicit formula, but we have everything to do that. We know it would be 5 times 2 to the n minus 1. One reason you might want to write this down is you could then go back and test. You could plug 3 into this expression here and make sure it comes out to 20. Plug 6 in and make sure it comes out to 160. Okay, another application problem. So this one says we have a population of fruit flies. They're growing in such a way that each generation is 1.5 times as large as the last generation. Suppose there are 100 insects in the first generation. How many would be in the 4th generation? Then it says round the final answer to the nearest whole number. We don't want a fraction of a fly there. Okay, so the first giveaway, how to do this problem, is the fact that it says that each generation is 1.5 times as large as the last generation. Those words right there indicate that we are dealing with a geometric sequence. It's the definition, to multiply the previous value by a fixed constant. So the 1.5 is representing the r value for us. Then the A1 value, the starting value, is 100. So that gives us everything we need to write our explicit formula. A sub n is A1 times r to the n minus 1. So you end up with A sub n equals 100 times 1.5 to the n minus 1. This will model the population after just each generation. It's not a certain time, it's just numbering the generation. So this is the population of flies in the nth generation. All right, they want us to find what is the population in the 4th generation. So that would be A sub 4, which is 100 times 1.5 to the 3rd power. And these are going to get messy. I would just go straight to your calculator for that. This comes out to 337.5. And this represents flies. So remember, we don't want a fraction of a fly, so they said round to the nearest whole number. This is going to round up to 338. So 338 flies in the 4th generation. Okay, last topic is geometric means. And this is going to work the same way that it did for arithmetic means. The geometric means are just the terms between two other terms in a given sequence. So right here I have an example of a geometric sequence. And suppose you were given the number 2, you're given the number 162, and they say find 3 geometric means between them. These would be the 3 geometric means, just the terms in the sequence between the 2 given ones. Okay, so let's try applying that down here. We are given a geometric, we want to find the geometric means between these 2 numbers in a geometric sequence. So let's make a little picture of that. So 2.25 is one term, then you have 3 missing terms, and then you have 576. Okay, so we have 2 methods again that can be used to solve this, but I'm going to use what I would consider the shorter method, similar to the second method that I taught for arithmetic means. So the idea is this: if the sequence is geometric, then to progress, I have to just keep multiplying the previous term by r. So in other words, this blank is really 2.25r. But then I take this number and multiply it by r to get this one, which is 2.25 r squared. I had to multiply by r twice to get here. This one would be 2.25 r cubed. And then finally, this number has to be 2.25 r to the 4th power. Right? We multiplied by r 4 times to get to this place. So that's an equation. We can say 576 has to be equal to 2.25 r to the 4th. Okay, so now we just need to solve this equation for r. Now it's important here to follow order of operations. In this equation, we need to get r by itself, but in order to do that, we need to get rid of this coefficient before we deal with the exponent. It's going to be much cleaner if we move this first. So to move this to the other side, I got to divide both sides by the 2.25. 576 over 2.25 equals r to the 4th. If this doesn't come out nice, then I would leave it the way that it is, but for this particular problem, that does divide nicely and gives you 256. Now we have to get rid of that power. So just like we did before, we're going to take a fractional power of both sides. So 256 to the 1/4 is equal to r to the 4th raised to the 1/4, taking a 1/4 power on both sides. In other words, we're taking the 4th root of 256. And then over here, these powers are going to cancel, so you just end up with r there. And that comes out nicely to 4. And so this gives us enough to go back and fill in those missing numbers. So we need to take 2.25, multiply it by 4. That comes out to 9. To get the next one, we just multiply the 9 by 4, which is obviously 36. Multiply by 4 again, and we get 144. So these are the 3 geometric means that they were asking for: 9, 36, and 144. All right, I believe that completes this section, so hopefully this was helpful. If you are struggling with any of the concepts, make sure you are contacting your teacher.